So good morning, cadets. Good morning. So for our first task for the day is there is going to be a grid and there are going to be anywhere from 4 to 8 enemies. All you have to do in the tank is observe. You have to go close to the enemy, observe, take a picture and then dodge them. No attacking, no hitting the enemies. That's the task, cadets.
Lieutenant Guard.
The robot uses a task-centric free RTOS architecture to separate communication, sensing, decision, and actuation. The communication task is interrupt-driven. It receives a 7-character command, parses it via the command parser, and posts the entries into the command queue without touching any raw hardware first. The control tasks handle the following: accessing the command queue in short intervals, supervise the shared data access, and update the motion goal state machine. After processing the command, the motion goal state machine uses goal-sensitive functions which are converted into raw motor tasks which are fed into the motor queue. Sensors run using the RTOS timers, which either set a flag or release a semaphore, which then wakes up the dedicated sensors to perform reads and update the shared data. This creates a modular free RTOS system.
We begin with the IMU, which tracks the robot's yaw angle using a complementary filter that fuses gyroscope and magnetometer readings. This allows for fast angle detection with near-zero drift. For straight line motion, we implemented a servo correction mechanism. Once the robot deviates, the servo automatically adjusts its path, eliminating the need for a PID controller. For turning, we tested several approaches, including normal 90, 45 degree, and two-step 45 degree turns, but ultimately reverted back to the standard 90 degree turn for better accuracy and reliability. Finally, for wall hugging in Task 2, we use a combination of IR sensors, ultrasonic sensors, and gyroscope feedback to maintain a consistent distance to the wall. The IR sensors provide close-range precision, and the ultrasonic sensor detects wider gaps or obstacles ahead, and the gyroscope ensures smooth orientation control. Together, these systems enable the robot to move stably and continuously along walls, even around corners.
The RPi serves as the main hub for sending and receiving messages from the different services, so it has to talk intimately with all of the different components: Android, image recognition and algo server, and the STM board. This shows the overview for the pipeline for message sending. I'll use Task 1 as an example. In Task 1, the Android first sends a start message to the RPi, which then sends a request to the algo server, which responds with the path. The path is then received by RPi in the form of suitable STM commands and sent to the STM board for movement. During the pathfinding, there are also commands to tell the robot to snap an image, which is then sent to the image recognition server, and it responds with the detected text, which is then sent back to the Android to be displayed on there.
So we trained our YOLO V8 model based on datasets that we found online, such as RoboFlow, and also on self-collected dataset, as you can see in this animation here. Here's a demonstration of our image recognition at work. So there are two challenges that we faced during this task. First was that when the camera was tuned into the image, we were unable to capture the numbers or the arrows. Hence, we had to create training samples using self-collected datasets with the camera near to the image. Second was that the image recognition was poor with colored images or images with patterns. Hence, we created our own color backgrounds with glare and also added a grayscale and high contrast filter on top of these datasets so that the camera would not be affected by the color backgrounds.
For Android interface, we have separate controls and tabs for each of the given tasks, and one of the special features of our interface is that we added a light and dark mode toggle feature for user preferences. For Task 1, we can set obstacles on the grid map easily by clicking onto the grid map directly, and you can adjust it easily by dragging them around. You can also easily remove obstacles by simply dragging them out of the grid map. Some quality of life features that we added were reset arena button to clear the entire arena and a function to insert obstacles with the X and Y coordinate. The obstacle list is also shown so that the user can easily verify the obstacles are in the correct place. We also added manual controls to control the robot manually and included an outdoor arena toggle button, as we realized that the turning radius for outdoor flooring is different and the stopping distance is also different as well. Hence, this information will be relayed to the algo server to find the most appropriate path. For Task 2, since we do not need to input anything, we just have a big gun button to start us off.
For the algorithm, our tank is simulated as a 3x3 block starting at the bottom left of the arena. Once our enemies are located with the direction they are facing, we set the optimal viewpoint as 2 tiles away, then use the A* search algorithm to compute the optimal path between all viewpoints and the start, penalizing turns and moves that places the tank too close to the enemy. Afterwards, we solve the traveling salesman problem to figure out the shortest possible route that visits all our targets.
They ask you how you are, you just have to say that you're fine when you're not really fine.